What if the future of energy didn't lie in the ground beneath us, but in the sky above? What if we could capture power where the sun never sets, where there's no cloud cover, no nightfall, and no interruptions? It sounds like a science fiction dream. But this idea, the concept of harvesting solar energy from space and beaming it down to Earth, has quietly become one of the most ambitious megaprojects ever conceived by humanity. And it's already under development. This isn't about another solar panel farm in the desert. This is about building an energy system in orbit, kilometers wide, that could generate continuous, uninterrupted clean power for cities, countries, and even entire continents. If successful, it could solve the global energy crisis, eliminate our dependence on fossil fuels, and fundamentally shift the geopolitical balance of the world. This is the megaproject that could change Earth forever. Despite rapid growth in renewable energy, the truth is that ground-based solar still has serious limitations. Solar panels on Earth are constrained by factors we cannot control. They only work during daylight hours. They lose efficiency on cloudy days, in regions with long winters, or during extreme weather events. And even when the sun is shining, the atmosphere filters out a large portion of the incoming solar radiation before it reaches the panels. Storage remains a major bottleneck. Even the most advanced battery systems struggle to retain enough energy to power cities overnight, let alone during seasonal shifts. And as energy demand increases globally, especially in emerging economies, earthbound solutions may simply not scale fast enough. So the question becomes, what if we could bypass those limitations altogether? In the 1960s, scientists began to wonder whether solar energy could be collected not on Earth, but in space. Above the atmosphere, sunlight is constant and unfiltered. In geostationary orbit, approximately 36,000 kilometers above Earth, a satellite can remain locked above a fixed point on the planet, continuously facing the sun. From that vantage point, an orbiting solar power station could collect solar radiation around the clock, convert it into electricity, and beam that energy back down to Earth using either focused microwave transmission or high-intensity lasers. On the ground, massive receiver arrays, called rectennas, would then convert that energy back into electricity and feed it directly into the grid. The physics works. The engineering is daunting. But with modern launch systems, materials science, and wireless transmission technologies, this concept is no longer a fantasy. It is now a race. Japan is currently leading the way. Through its National Space Agency, JAXA, Japan has been investing heavily in a project called the Space Solar Power System, or SSPS. In 2015, JAXA made headlines when it successfully transmitted 1.8 kilowatts of electricity wirelessly across a distance of 50 meters using microwaves. While that is a far cry from powering a city, it was a historic proof of concept that validated the core principle of space-based solar power. Japan's goal is now to deploy a fully functional 1 gigawatt orbital solar station sometime in the 2030s. For reference, 1 gigawatt is enough to power hundreds of thousands of homes. Their envisioned satellite array would span multiple kilometers and require robotic self-assembly in orbit. Once deployed, it would transmit energy 24 hours a day to Earth-based receivers, making it the first truly continuous renewable energy source. Japan is not alone in this endeavor. Around the world, countries are waking up to the potential of orbital solar power and investing in their own initiatives. China is developing its Chongqing Space Solar Energy Station, with a goal to deploy a megawatt-level demonstration satellite by the end of the decade. Their longer-term vision, set for 2050, includes gigawatt-scale power stations capable of transmitting energy across continents. They have already built a test base and successfully conducted high-altitude wireless transmission trials. The United States is pursuing its own version through a Department of Defense program known as SPIDER, short for Space Power Incremental Demonstrations for Energy Reliability and Supply. The project is focused on developing scalable, modular satellites that could one day beam power to remote military outposts, forward operating bases, or disaster zones. In the United Kingdom, the Space Energy Initiative is a growing consortium of academics, engineers, and policymakers. Their goal is to launch a fully functional space-based solar station by 2040, one that could eventually supply up to 20% of the country's total electricity demand. This is no longer a fringe idea. It is an international engineering race, one that will decide who controls the energy infrastructure of the 21st century and beyond. So what exactly would a functioning space-based solar power station look like? Imagine a structure the size of a city block, orbiting far above Earth. Its surface is covered in ultra-thin, ultra-efficient photovoltaic panels. These panels convert sunlight into direct current electricity. That electricity is then transformed into microwave or laser radiation by an onboard converter and aimed with high precision at a ground-based receiving station. These receiving stations, called rectennas, are large, open fields covered in metallic mesh. They absorb the incoming energy beam and convert it back into usable power, which is then transmitted to homes, businesses, and infrastructure. The entire process is wireless, safe, and, if properly calibrated, more efficient than most Earth-based solar setups. In geostationary orbit, the satellite never moves relative to the Earth, meaning the beam remains fixed on a single target, allowing for consistent delivery and minimal energy loss. Of course, building something of this scale is not without its difficulties. The first and most obvious challenge is cost. Launching thousands of tons of equipment into orbit remains extraordinarily expensive. Even with cost reductions from reusable rockets, the budget for a single gigawatt-class solar power satellite is projected to be in the tens of billions of dollars. The second challenge is safety. Any system that transmits energy wirelessly, especially at high intensities, must be tightly controlled to avoid any risk to aircraft, satellites, or human populations. Microwave and laser transmissions must be precisely tuned to avoid interference and ensure environmental safety. Third, there is the issue of orbital congestion. Geostationary orbit is already crowded with communication and weather satellites. Adding massive solar arrays into that space will require international coordination, regulatory frameworks, and new standards for orbital traffic management. Finally, there are political challenges. Who will control these stations? Will the energy be sold to the highest bidder? Will this technology be used to help all nations, or to give dominant ones yet another strategic advantage? Despite the obstacles, the potential upside is staggering. If fully realized, space-based solar power could provide limitless clean energy to any part of the world. It would be especially transformative for regions without stable infrastructure, remote islands, developing nations, or areas affected by disaster or war. It could reduce global carbon emissions dramatically. By replacing coal, gas, and oil plants with orbital solar arrays, we would eliminate one of the largest contributors to climate change. It could also reduce energy inequality. For the first time in history, a village in the middle of the desert or deep in the rainforest could receive high-bandwidth energy without needing roads, power lines, or fossil fuel deliveries. And it doesn't stop there. The infrastructure needed for space-based solar could eventually power bases on the Moon, on Mars, or aboard deep space missions. In fact, some experts believe orbital solar power is a prerequisite for long-term human settlement beyond Earth. What we are witnessing is more than just a technological shift. This is the beginning of a new relationship between humanity and energy. For the last 200 years, our progress has been tied to what we can extract from beneath our feet: coal, oil, gas. But with space-based solar power, we flip that dynamic. Our future energy source lies not in extraction, but in collection. Not in depletion, but in abundance. It will take unprecedented collaboration, political vision, and technical ingenuity. But if we succeed, the rewards could be historic. We would no longer be bound to the limits of the Earth. We would, quite literally, be powered by the universe. This is not a hypothetical. The research is happening. The tests are underway. The timelines are being drawn. By 2035, we could see the first commercial orbital solar station beaming power to Earth. By 2050, space solar could be a trillion-dollar industry, and the foundation of all future energy systems, both on Earth and in space. It is a megaproject unlike anything we have ever attempted. And if it works, it could change the world forever.